In Module 4, we're going to talk about chemical reactions and reactions that occur in aqueous solutions. So for 6.1, our learning outcomes are to understand the nature of water's role in solvation. Now, water is a polar compound. What that means is it acts as if there are tiny magnets in the water molecule. One end is a positively charged end, one is a negatively charged end. When water interacts with an ionic compound that is soluble, the different ends of the molecules orient themselves around the different ions. So in water, the negative end of the water molecule is the oxygen atom. That will be attracted toward the positively charged cation in our soluble salt. The hydrogens, which are positively charged, are going to orient themselves around the anion to try to mitigate that charge. Now, once this happens, going from an original crystal lattice, now we have solvent-separated ion pairs. Solvent-separated ion pairs. These are free to move about through the solution. Now, when you can have charge moving about, this will be able to conduct electricity. Ions aren't the only thing that can be solvated by water. When we take something like ethanol, a molecule that has a polar bond in it, in this case the ethanol has an OH bond, that can interact with the water molecule in much the same way. The negative end of the water molecule will help solvate or be attracted to the positive end of your ethanol molecule, and additionally the positive ends would be attracted toward that negative oxygen on the ethanol molecule. And this is because polar compounds are dissolved by polar solvents. It's what we call like dissolves like. Nonpolar compounds would be dissolved in nonpolar substances. Now, we're not really worried about the whole nonpolar to nonpolar bit at this point. What we really want to understand is water, being a great solvent, will tend to dissolve a lot of different things, and it is based on that polarity. Continuing to talk about things dissolved in water, we have to come up with some definitions. The solution is a homogeneous mixture of two items. In the case of, say, salt water, we have two components to this. We have the solute, which is the substance that is present in lesser amounts, and the solvent is present in greater amounts. Usually when we talk about aqueous solutions, water is our solvent, and anything that is dissolved in the solvent is the solute. Now, we also need to know how much solute is in our solutions. We do this in terms of concentration. And concentration is the amount of solute per amount of solvent. There are many different types of ways to express concentration. In fact, if you think about it, density, which is a mass over a volume, is really a concentration of matter. How much matter in terms of mass per some unit of volume. We will look more at concentration units as we do more mathematical representations of solutions. In section 6.2, we're going to be able to identify strong, weak, and non-electrolytes by formula, discuss the strength of electrolytes in terms of the electrical conductivity, and define acid and base under Arrhenius. So an electrolyte is a substance that produces ions in an aqueous solution. Now, electrolytes can be strong or weak. Strong electrolytes are when the ions are completely dissociated in water. That is, they form these solvent-separated ion pairs. That's what we saw earlier in the sodium chloride example. You may also have weak electrolytes. Weak electrolytes are ions that are partially dissociated, but mostly the compound exists as molecules in solution. An example of this would be any of our weak acids. We memorized the strong acids in order so that we didn't have to memorize all the weak acids. So anything that's not a strong acid, which, by the way, are strong electrolytes, would be weak acids, which would be weak electrolytes. So something like HF, hydrofluoric acid, is a weak electrolyte. When I dissolve HF in solution, that's what the 8Q means. When I dissolve HF in solution, it dissolves to form H plus ions, aqueous, and fluoride ions, aqueous. But this reaction isn't exactly a one-way ticket. In fact, it is a reversible reaction. And most of the molecules of HF stay undissociated. Hence, this is a weak electrolyte. Additionally, you may have non-electrolytes. These are substances that, when dissolved in water, do not produce any ions. These are often molecular compounds, which contain OH, oxygen, nitrogen, or NHX groups. NHX is just a generic term for the amino group, with X being a number 1 or 2 or possibly 3 even. Now, ethanol, which we had seen before was C2H6O, this did not produce ion pairs. No solvent-separated ions, no ions at all. This is a non-electrolyte. The way you can absolutely determine whether you have an electrolyte or the extent of the electrolyte solution is by measuring its conductivity. The higher the conductivity, the stronger the electrolyte. The lower the conductivity, the weaker the electrolyte, and if it does not conduct at all, you have a non-electrolyte. This is what we see in figure 6-4. In a strong electrolyte where all of the ions are separated, electricity flows quite rapidly. When we have something like HF, where we only have a couple of ions, most of the molecules stay together, we have a very dim light bulb. And if we have something like sugar, which doesn't dissolve to give us ions, there is no conduction through the solution. Now, we hinted on this with acids and bases. When we talked about nomenclature, we learned what the acids and the bases were and how to recognize them. Now, acids and bases can be defined under several different definitions. In this chapter, we're actually going to talk about several definitions, but the first one we want to talk about is the Arrhenius definition. Arrhenius was a chemist who worked on electrolyte solutions and developed a theory of acid-base chemistry. He proposed that a substance that produces H plus ions in water is an Arrhenius acid, and a base would be something that produces hydroxide ions in water. So, for example, if I put HCl in water, I form H plus ions and Cl minus. Hydrochloric acid is indeed an acid. If I were to put sodium hydroxide into solution, I will produce hydroxide ions in water. Therefore, this is an Arrhenius base. The strength of the acids and bases depends upon how much they dissociate. A strong acid or a strong base dissociates completely in solution. Weak acids and weak bases dissociate only partially. So here we have acetic acid in figure 6-8. Acetic acid or vinegar exists mostly as the molecular form. Only a few molecules in every 100 molecules, I believe it is around 5 or 6% of those guys are ionized. So most of them, 95% or so, stay as molecules. Therefore, acetic acid is a weak acid. Additionally, something like ammonia, NH3, which does not contain any hydroxide ions. When this is dissolved in water, it actually pulls a proton off of the water to form the ammonium ion, and that extra leftover bit is an OH ion, the hydroxide ion. Only a small fraction of ammonia in water does this dissociation between the NH4 and the OH minus ions. So let's put what we've learned to the test. Show how each of the following electrolytes breaks up into component ions upon dissolving in water by drawing molecular level pictures. So let's start off with sodium bromide. Sodium bromide is much like sodium chloride. You have the sodium ion and the bromide ion. Now if I draw a molecular level picture, it would be like two spheres of opposite charge being attached to each other. When these get dissolved in water, they break apart into our sodium ion and our bromide ion, and we have water molecules. Now, the ends of the water molecules that are going to be attached to the sodium is the negative end. In this case, the oxygen end. So I'm only going to draw a couple of the water molecules surrounding that, but it would fully surround that sodium ion. The bromide would be surrounded by the hydrogen end of the water molecule. So let's try the next one, magnesium chloride. If we draw magnesium chloride as a series of spheres, we have one magnesium 2+ ion and two chlorides. When this dissolves in water, the magnesium ion, which is the cation, will be solvated by the oxygen ends of the water molecule. The chlorides with two of those guys coming off would be solvent separated not by the oxygen but by the hydrogen ends of the water molecule. I'm only going to draw a couple there to illustrate that that's what happens. Let's move on to something that's a little bit more complex. Let's try the ammonium acetate compound. If I were to draw a molecular level picture for ammonium acetate, I would have the ammonium ion and the acetate ion. Now the ammonium ion, when we dissolve it in water, is going to break apart to form the NH4+, and that again is going to be solvated by the oxygen end of water molecules. But when we take a look at the acetate portion, it's really this oxygens at the end of the acetate ion that are going to be dissolved by water, much like we had with the ethanol molecule. So if I draw this in proportion, C2H3O2 with a minus, really my hydrogens are going to solvate that O2 portion and leave the C2H3 portion alone. So I hope if you give these a shot that you will be able to determine strong versus weak electrolytes and non-electrolytes, and strong acids and weak acids. Remember your strong acids and your strong bases. And think about whether you have a strong acid, a strong base, a weak acid, a weak base, or a non-electrolyte with every item you come into contact with. Additionally, if it's not an acid, try to think to yourself, is this a molecular compound or is this an ionic compound? This is where nomenclature and all the work we've done up to this point comes in really handy.